My name is Diane Call. I have the privilege, a distinct privilege, to lead this institution and welcome you to our spring 2018 presidential lecture. As you know, for many of you who've been here before, and this audience includes students and faculty and staff and members of our community, this series was launched back in 2000 by my predecessor, Dr. Eduardo Marti. And in the fall, we always focus on someone in the City University of New York or higher education. And in the spring, which I have to tell you is my favorite season, it's one of our own faculty. And it's a pleasure to showcase our faculty. And it's a very hard decision because we have over 400 full-time faculty and about 500 adjunct faculty from whom to choose. And I want to thank the committee, the Presidential Lecture Committee, Dr. Tim Lynch, who's our provost and senior vice president for academic affairs, and Dr. David Humphreys, who chairs our English department, and he himself was a presidential lecturer in 2008, and Dr. Azi Alai from social sciences and psychology, and Dr. Paul Sideris from our Department of Chemistry. So thank you, committee members, and let me just tell you a little bit about our very distinguished lecturer today. I'm really honored to introduce Dr. Jillian Bolivari. She is an assistant professor in our Department of Physics, and in her astronomy classes, Dr. Bolivari uses Einstein's predicted gravitational waves to encourage student learning about space and the discoveries of massive black holes. And we've heard so much about that, especially with the recent passing, of course, of Stephen Hawking. Her teaching fosters true student engagement. And it's amazing because our students are naturally very curious, but I'm sure many people are a bit daunted by the thought of studying science. And to her credit, Jillian does a great job of making sure that they are truly engaged and active. She mentors many students in terms of research. She focuses and encourages them to look at evidence, something we should all do these days in the search of truth. She has them doing all kinds of activities so that they can understand the nature of exploring an idea and finding how it does play out. So in addition to teaching at Queensborough, Dr. Bolivari serves as a resident research associate at the American Museum of Natural History, and she's also a member of the Committee on Status of Minorities and Astronomers of the American Astronomical Society. She holds a Bachelor of Science in Astrophysics, Physics, and Philosophy from the University of Wisconsin-Madison, and a doctorate in astronomy from the University of Washington. So please join me in welcoming Dr. Jillian Bolivari.
All right. Thank you, President Call, for the lovely introduction, and thank you to the committee for nominating me. It's really wonderful to be here. Thank you all for coming. It's great to see you all. So, a show of hands first. How many of you have heard of gravitational waves? Okay, that's pretty good. How many of you are like, what the heck? Okay, that's also pretty good, because it's important to be honest. So this lecture is about what in the universe are gravitational waves and why should you care. But before we talk about what gravitational waves are, let's talk about something called space-time. Space-time is this sort of weird fabric of the universe that normally is pretty flat, but it bends when something is really massive. So if you imagine that you have like a sheet, and you hold it out and you stick a ball in it, the sheet will bend a little bit. And then if you stick a heavier ball, I don't know, a basketball in it, the sheet will bend more. And then if you get a bowling ball and put that in it, the sheet will bend a lot, like this right here. And that's a good analogy for what happens around a massive object like a black hole, or even a less massive or more normal object like our sun. It actually bends space-time so that space becomes long and weird around objects like black holes. And that is part of why black holes are so darn strange, because they bend time and space around them. And so what gravitational waves do are waves in this space-time fabric. So you can imagine waves going through this. It's kind of like a drop of water in a puddle, except that instead of the surface being water, the surface is the space-time fabric of the universe. So another way to imagine it is if I have my trusty yardstick here, and let's say that President Call and I are 1 meter apart, and what if a gravitational wave comes by? So first of all, we can't feel gravitational waves. They're much too weak. And so if a gravitational wave comes by, we will not know. There's probably one going by right now. We don't know, and that's fine. That's for the best. But if we were to feel it, we would stretch in space-time, but also squish in space-time, kind of like what's going on here. A gravitational wave stretches and squishes space-time in this like sort of multi-dimensional way. So President Call and I would sort of be like, whoa, like this, except that it wouldn't really be me moving back and forth. It would be the meter stick stretching, getting longer and shorter and longer and shorter. The meter itself changes length. A meter gets longer and a meter gets shorter because space is expanding and squishing. So that's what happens when a gravitational wave goes by. Here's a movie of a really, really exaggerated situation. Let me push play here. We've got the Earth, and there are some sort of green waves coming from this corner. Those are simulated gravitational waves, and the Earth is stretching and squishing in a very exaggerated way. This is not what would really happen. And there, our gravitational wave event has gone by. So you could kind of get a feeling of what goes on when gravitational waves come by. So what types of things emit gravitational waves? How do you get them in the first place? Well, the thing that I'm going to talk about is merging black holes, because merging black holes are my favorite kind of thing that emits gravitational waves. But there's some other stuff too, merging neutron stars, or merging black holes and neutron stars, or supernovae, which are exploding stars, the Big Bang, the beginning of the universe, and maybe even some other stuff that we don't even know about. I like to say that question marks emit gravitational waves, because we don't even know what is out there that's emitting gravitational waves. So I'm going to talk about black holes, and I want to first go, what is a black hole? Now, a lot of people, when they're like, what's a black hole? They think, oh, it's like this cosmic vacuum cleaner. Shown here is a picture from the movie Spaceballs, which is a great movie. But it isn't really a cosmic vacuum cleaner. It's not this thing just moving through space, just like sucking up everything in sight. That's not really what it's doing. Really, it's just a lot of gravity. And we're familiar with gravity because we live on Earth, and gravity is very helpful to us. For example, if I jump up in the air, gravity pulls me down again, and that's good and normal. And we know that if I wanted to escape the Earth's gravity, I would have to jump really, really fast and high, which I, of course, cannot do, but a rocket can do that. So if you have your rocket and you give it enough speed, it can escape the Earth's gravity. And that speed that it needs to escape is called the escape velocity. So if you have your rocket and it's awesome enough, and you're Elon Musk and you stick your car on it or whatever, you can get it up into space and send it wherever you want to send it. So you have to overcome gravity. So black holes really have a lot of gravity. They're really, really heavy things, and in a very small amount of space. And what makes them so interesting is that the velocity you need to escape a black hole, like if you had your rocket on the black hole and we're trying to launch it off, which you can't do, but pretend, bear with me, is that the escape velocity of a black hole is faster than the speed of light. And the speed of light is the fastest speed there can be in the universe. And so that means that nothing can be faster than the speed of light, which means nothing can escape a black hole, not even light. So instead of your rocket escaping, your rocket would fall back into the black hole, along with everything else that's nearby. So really, if you're close to a black hole, that's a bummer, and you fall into the black hole. But the same thing happens if you're close to Earth. If you get too close to it and you're orbiting, you'll fall in and you'll land on it. It's just that a black hole does extra weird things like bend space and time and emit gravitational waves. But really, it's just a whole bunch of mass, not a vacuum cleaner. So there are a couple types of black holes that I want to talk about. One type is what I call the stellar black hole. A stellar black hole has a mass of between 1 and 100 solar masses. What is a solar mass? A solar mass is the mass of the sun. And if you want to know it in kilograms, it's this many kilograms, which is why I don't write this on the board anymore. Instead, I write solar mass. That is our new unit of mass, because you can't count all those zeros. There's 30 zeros there. Okay. So a black hole that's called a stellar black hole is between 1 and 100 times the mass of the sun. We know that these form when stars die, when they go supernova. And we know that these are located pretty much everywhere stars are located. So they're like in galaxies hanging around wherever stars are hanging around. And there's another kind of black hole called a supermassive black hole. This one is much bigger. It's between 1 million and 1 billion times the mass of the sun. So it's huge. These are located in the centers of galaxies. There's one in the center of our Milky Way that's about 4 million times the mass of the sun. And we don't actually know how these form. We have a few ideas, but they're all a little wacky. There's no sane ideas. Does anyone notice something weird about these two types of black holes? Something missing?
A whole lot of mass.
A whole lot of mass is missing?
A whole lot of mass.
Yeah, where is it? Kim, what did you want to say?
Well, somewhere between 100 and 1 million, there's a lot of stuff.
Yeah, there's like, between 100 and 1 million, there's a big gap. Like, are there medium-sized black holes, or what we call intermediate mass black holes? Because between 100 and 1 million, there's a lot of space there for there to be mass. So like, what's up with these? So I want you to remember this, because we haven't actually found any, but that doesn't mean they don't exist. I think they exist. So keep that in mind. So these are our two types of black holes. So let's get back to gravitational waves. How do we detect gravitational waves? Well, it's tough, because you can't feel them, right? And so that you can't do that. You definitely can't use a ruler. I've already explained how your ruler stretches along with space-time, and so you can't use your ruler. You definitely can't use a telescope, because it's not light. So what are you going to do? You need to use something that doesn't change when space-time ripples. And it turns out that light is actually very helpful, because light, the speed of light is always constant. And so we can use that fact that when space-time ripples, the speed of light will always be the same. And so when in doubt, we use lasers, because lasers are cool. And it turns out that there's a special property of light that's really helpful. That's called interference. So I want you to look at these little graphs over here. Light has this sort of wave shape to it. And if you have two pieces of light where the waves are lined up, they can add together and make a taller wave of light. But if you have them so that they're anti-aligned, they can cancel each other out. This is called destructive interference. And they make no light. Okay? And so we use this interfering property of light to help detect gravitational waves by building something called an interferometer, which is basically measuring how the light interferes, an interferometer, but it's called interferometer. And so I'm going to go through this sort of contraption for you. But basically, we built something called LIGO, which is a giant interferometer that helps us measure gravitational waves. Here is a picture of LIGO. There's one LIGO in Washington State, and there's one LIGO in Livingston, Louisiana. And there's actually one now in Italy called Virgo that is up and running as well. So there are 3 of these. And they're pretty big. So these arms of this interferometer are 2.5 miles long. So that's pretty big. You need a big open space. You can't build this in New York City. There's no room for that. But you can build it in the middle of the desert or in the middle of the swamp. and nobody seems to mind. So how does LIGO work? I'm going to show you how this interferometer works with this cool little movie. All right, so there's a laser, and it bounces off of some mirrors, but these mirrors are attached to these wiggly things. So what's going on? So let's zoom in. Here's our laser going through, and it bounces off of this mirror right here. And it combines again with the laser coming from the other mirror onto this detector. And remember how light can interfere? If the light is together in phase, it will add, and if it's opposing, it will cancel. And as these move back and forth, you can change the pattern here, if they're adding or subtracting. See how this little pattern is changing. And so on these mirrors, we put our gravitational wave detectors. On these mirrors are actually this kind of contraption here, where this is where the mirror is, and it's hanging from a pendulum, which is hanging from a thing, which is hanging from another thing. It's this whole long thing of things. But what this does is it makes this mass wiggle back and forth if a gravitational wave hits it, but it damps out other perturbations. So like, say there's an earthquake, or a truck goes by, or there's a tsunami in the ocean not too far away. Those things will all shake the Earth a little bit, but all this series of pendulums will all stop this from wiggling back and forth unless there's an actual gravitational wave coming by. That gravitational wave will cause this to move, which will cause the laser interference pattern to change. So that's how we detect gravitational waves, basically with immense feats of engineering. And this is really hard. This is something Einstein thought of in 1915. And in the 60s, people were like, hey, maybe we could build it. And in the 90s, people sort of started to build it. And then in the 2000s, people were like, we built it, but it doesn't work yet. But if we upgrade it, it will work. And now it finally works, 100 years after Einstein thought of it. It needs to be extremely precise. It needs to be so precise that if we were measuring the distance from us to the nearest star, it would need to be as accurate as the width of a human hair. Or another way to put it, it's a very small fraction of the diameter of a proton is what is actually being measured. So it's really, really hard to make this measurement, which is why it has taken so long. But the measurement has been made. So what does it do? What do we see? So here's a graph of what merging black holes look like from LIGO. It looks like a squiggly line. Let me explain this squiggly line to you. So this is showing here, oops, there we go, is this is the amount, this thing called strain here is the amount that the detector wiggles when the gravitational wave goes by. And this is versus time. So as time goes on, it's like a little bit wiggly, and then it gets more and more wiggly, and then it stops. So that's how much the detector is moving. This is the Washington one, and this is the Louisiana one, and they match each other. And they match the models of merging black holes that are predicting what's going on. And so this was the first detection of merging black holes that happened 3 days after we turned on LIGO. They were like, whoa, really? Yes, it really happened. And since then, several other merging black holes and even some merging neutron stars have been detected, all from these little wiggly lines that are basically we have things moving back and forth, and we can tell from that black holes are merging somewhere in the universe, which is super cool. This detection has actually been translated into sound. Now, gravitational waves are not sound because they're space-time, and sound is not space-time. Sound is vibrations through a medium that hits our ear. But the sound is, or the frequency of the gravitational waves is actually at the same frequency that our ears can hear. And so this little video of this detection has first the gravitational wave detection playing in the actual frequency, and then sped up a little bit so that we can hear it a little bit better. So you can hear what the gravitational wave detection sounds like. So it repeated a bunch of times. The first one was very low, kind of like a thump, and then it was like a higher one. And it was very quick. It was over in less than a second. The detection is less than a second long of these merging black holes. Here's another movie that translates the merging black holes into colored spacetime. So what the heck's going on here? This rainbow coloring represents spacetime, and the colors represent how much spacetime is bent. So here are black holes, and they're rotating, and they're merging. And there's these sort of pits here that are the bent spacetime. And as they get closer and closer together, the gravitational wave detection is down here, that wiggly line. Space-time starts to get weirder and weirder. We slow it down. Space is warping, bending. We freeze the movie, like, what the heck is going on? And the black holes coalesce. And space-time sort of sloshes back to normal. Just like everything's fine now. And there we are, our single black hole that is left over. So LIGO has been really great in allowing us to learn a lot about black holes. So this is a little picture of mass going up here. All these blue black holes have been discovered by LIGO. They're all mergers that LIGO has seen. And that adds to the purple black holes are ones that we knew about before LIGO. And so the most massive stellar black holes, up to 80 solar masses, are all things that we've learned about by LIGO. We didn't even know that there were black holes this big, much less two of them together that were smashed together. We didn't even know. And there's no way to see this with a telescope because black holes are black, and so they don't emit any light. So there's no light coming from these merging black holes. At least we don't think there is. There shouldn't be, according to Einstein and Stephen Hawking and all the other smart folks who've thought about this a lot. There should not be any light coming from it. So the only way to learn about these is through gravitational waves. But what about these supermassive black holes that I mentioned earlier? Those aren't on this graph because LIGO can't actually see them. LIGO can't do everything, it turns out. It's super great, but it can't do everything. And it's because gravitational waves have different frequencies. Just like how sound has different frequencies. For example, if you blow your dog whistle, your dog can hear it, but you don't think anything is going on. Your dog just magically comes to you, hopefully. Also with light. You don't see Wi-Fi. That would be weird. It would be all over this room. And you don't see, for example, X-rays. But we know that they're there, just that our eyes can't detect them because they're in a different frequency from what we can detect. So LIGO is similar in that it can only detect gravitational waves at certain frequencies. And that has to do with the size of LIGO. It's 2.5 miles on each of its arms of the interferometer. And so that means that it can detect gravitational waves that are like about that size. But what if the waves are a different frequency? So here's a little chart of all of the frequencies of gravitational waves, the gravitational wave spectrum. And here's LIGO, which can see this range of it. So it can detect pulsars and supernovae and compact binary in-spiral and merger. Those are our black holes. Those are our black holes that are smashing together, and the neutron stars and the other stuff. So LIGO can see things in this frequency range, but this whole other part is missing. LIGO cannot see the stuff going on there. And it turns out there's a bunch of stuff there. So for example, the supermassive black holes, those have a different frequency that's like over here. The Big Bang, we think, covers everything. There's some other stuff, extreme mass ratio in spirals, some other odd things. But basically, LIGO can't cover all of that frequency space. We need to build other detectors or find other ways to detect those gravitational waves. So the one I want to talk about is this thing, the space-based interferometer. So the one I talked about with LIGO is a ground-based interferometer. It's on the ground. The space-based one, we're going to put in space. In particular, we're going to launch it, and it's going to follow the Earth in this sort of cartwheeling triangle. This thing is called LISA, the Laser Interferometer Space Antenna. And it is going to detect merging supermassive black holes. It's going to detect things that are so far away that we can't even see light from that far away, from the very beginning of the universe. However, it's going to launch in the year 2034, which is fine because my career will be just set for me to be an expert on all of the predictions right when it launches. So this thing is an interferometer. It's got these arms. They're in a triangle instead of an L shape. It's going to be huge. This triangle is 2.5 million kilometers long on an arm. That's like more than 5 times the distance from the Earth to the moon. That's how big it's going to be. And it's going to trail the Earth's orbit. So it's basically orbiting the sun in this funky cartwheel thing. So there's 3 reasons that I know that this is going to happen. Because you might be like, 2034, that's not going to happen. Who does she think she is? 3 reasons that I'm sure this will happen. 1, gravitational waves have already been detected. So before LIGO, this was like, I don't know. It's a lot of money and a lot of technology. But now that gravitational waves have been detected, it's like, OK, fine, they're real. So that's great. 2, the technology for this is already proven. So there were 3 detectors in the triangle. In 2016, we launched one of them up into space to prove that the technology, the engineering technology, could work, that we could actually measure gravitational wave to the sensitivity that we needed to. And it beat all of the expectations. It did better than expected. So the technology works. 3, it's headed by Europe. So even if whatever happens to NASA, who knows, the Europeans probably have their stuff together and we'll get this thing launched. We hope. So what will LISA do? LISA will measure merging black holes from the beginning of the universe onwards. We'll learn about when these black holes formed, how often they formed, and how many of them merge, what galaxies they're in. Remember when I talked about the supermassive black holes, I said, how do they form? And I had some question marks. This will figure that out. This will figure out how they form. LISA will be able to tell us by how many of them merge and when and where. Okay. LISA will also be able to tell us if there are intermediate mass black holes. Because, again, we don't see them in our universe, but that doesn't mean they aren't there. Maybe they're hiding. Maybe they used to exist, but then they all grew into supermassive ones. LISA will tell us if there are intermediate mass black holes. So I'm super excited about LISA. Are you excited about LISA? Yes. Good. So why do I care? Well, my research is doing computer simulations of galaxies with supermassive black holes. So what does that mean? Well, first I take a bunch of equations, and then I stick them into a supercomputer. This is the supercomputer at NASA that I use. It's called Pleiades. It's very fast. And what comes out is a little mini universe. Basically, I simulate a box of universe, and then I can analyze the galaxies that are in my universe and compare them to the ones in the real universe. I can see how do these black holes form? Do they merge with each other? Do they interact with the stars, with the gas, with the dark matter? How does it all come together? I have here a movie of a simulation. I want to turn the lights off for this because it's really cool looking, and it will look better with the lights off. So here's one of my simulations. This blue stuff is gas from the early universe, although it changes color based on temperature. So the red is hot gas, and the green is sort of medium. And these little white blobs are galaxies forming in the early universe. There's one big galaxy that's going to end up like our Milky Way, and then there are lots of small galaxies that are surrounding it. And a lot of these galaxies have black holes in them. And so what I do for my research is I analyze the properties of these galaxies, this big one and the small ones, and I measure where the black holes in the galaxies are, and when they merge, and if they grow, and what they're doing. And I make predictions so that astronomers with telescopes can see if I'm right. You can turn the light on again now. Thanks. Good, it worked. So that's an example of one of my simulations. I have a bunch of simulations, and my goal is to make predictions both for LISA, about where the gravitational waves will come from, how many there will be, what kinds of black holes make them, as well as for people with telescopes. How can we find more black holes? Are these intermediate mass ones around? Can we find them? Oops. So here's an example of some results that some of my students have created. One of my summer students, Colleen Cleary from Hunter College, made some images of galaxies that host black holes in the simulation. So these are simulated galaxies. They're fake. They're not real. And they're pictured twice. This one is face on and it's edge on. Face on and edge on. So you can like spin them around and you can see what they're like. You can count all the stars. You can measure the gas and you can find the black holes. So there's a little cross that denotes where the black hole is in each of these galaxies. So she analyzed a lot of these galaxies for me over the summer. And my Queensborough student, Rayhan Shakib, who's actually at Queens College now, he measured the shapes of the galaxies that host the black holes. So this is a graph of density versus radius. Basically, it's saying how much stuff is there in the galaxy and where is it. So in these small radii, there's a lot of stuff. This is very high up. And then as you go out to the outside of the galaxy, you get less and less stuff. And the amount of stuff in the galaxy and the shape matched our predictions of what we think it should look like. So I have students, undergraduates, who are working with me to help me figure out what's going on with these black holes in these galaxies and helping me meet my goal of making predictions for LISA and for astronomers with telescopes to be like, how can we find more black holes? How can we understand more about them? So that's why I care. But why should you care? You should care because for the first time, we can get information from the universe that doesn't involve light. For thousands of years, humans have looked at the sky, and we've used our eyes, and then we've put our eyes into telescopes, and then we've done things with computers, but finally, we can get information through another source. Gravitational waves can tell us so much about the universe that we could never have known because it comes from dark things that don't emit any light, or from things that are so far away that we can't see their light. So this is a whole new frontier of science, and it's also just really cool. It's so cool. Isn't it cool? Yeah. It's cool. All right, thank you very much. Especially welcome questions from students. Just if you need encouragement.
Should I? Yes, I have a question. This is probably very stupid. It's probably very obvious, but I'm a novice in this field. I understand that these laser arms can detect the gravitational waves, but how do they locate the source of the waves, which you say you're locating all these new merging black holes and everything from, I don't know, it doesn't make any sense to me that just the fact that you see them, that you can identify that they're there, how does it show you where they're originating?
That is an excellent question. That's not a stupid question at all. It definitely seems weird that something with like some arms can detect something where you're used to like a telescope and then you point it and you figure it out. So part of the reason that we can figure out like the mass and the distance of the black holes is from that squiggly line that I showed on the graph. Is that when we make a model of that squiggly line, we can match it to the observation and try and figure out what is going on with the black holes. As far as where it is in the sky, though, I actually have another slide for that. It's really hard to figure out where it is in the sky. So this is a map of the sky, and each of these colored, like, worm shapes are estimates of where the black hole merger happened on the sky. Now, if you had a telescope, you'd be like, the thing happened here. And you would point to it, and you would see the light. But you can't point the interferometer, and so you can't figure out exactly where it is in the sky. You have this like weird shape of where you think it is. However, now that we have 3 of them, because the one in Italy came online, it's much better at finding, because it can, finding the objects, because it can triangulate, because there's 3, so you can make a triangle. So this little green blob, where there's 2 of them, is when the 3rd one came online and you could triangulate, you could do a much better job of finding where the thing is in the sky. Great question.
Okay, I understand that the speed of light has been measured down to a fraction of a second, a thousandth of a second. But I'm wondering 2 things. First of all, is there any slight variation in the speed of light itself under different conditions, or is it an absolute constant everywhere down as far as can be measured? And the other question I have is has a gravitational wave actually been measured? From peak to trough, how long would a gravitational wave be?
Okay, first question. The speed of light, as long as it's light moving in a vacuum, there's no evidence for it varying. Once the light travels through a different medium, like water or glass or other things, it slows down. But the speed of light in a vacuum has no evidence for changing. How long does the gravitational wave take to go by? Where is the frequency graph? I don't know off the top of my head, but I can figure it out. Let's see. Milliseconds are the ones that LIGO saw, but they can be up to hours and even years, the period of the waves, depending on what's going on. So it depends on the frequency of the waves. For smaller objects like these small black holes, it's much quicker. And for supermassive black holes, it's much longer, for years or months or days or hours. It depends.
Yeah, hi, okay. So right now the technology just reminds me when we first started to, clock, graph sound waves and radio waves and X-rays, and we had this 2D kind of, wavy line. But right now we have X-ray telescopes, and many years later, we've been able to actually map and see 3-dimensional objects with these rays. So I'm wondering, is there any thought or research going on in terms of stacking or making some kind of cross matrix of these lasers and trying to get like a 3D image of the event?
Not that I know of. I am not sure that the more lasers you add, the more complicated it gets and the harder it is to deconvolve any gravitational wave signal. So I'm not sure about the feasibility of that, but it's an interesting idea.
Good afternoon. LIGO and eventually LISA are able to detect the waves, and what do these waves tell us about not only where we are in relation to the universe, but what do these waves exactly tell us about how the universe was formed and what else is going on in relation to us?
So far, they tell us that there are definitely more things than we know about in the universe. So there are black holes and maybe even other things that we can't see with our eyes that exist. And they seem to be pretty rare, though. Like, they're not going to come smashing into us anytime soon, so we're not in danger. I think and also we can learn about things that happen in the very early universe and learn much more about how it formed as soon as LISA is launched and goes online. Because a lot of that is very hard to figure out, because we can't watch it form. It was too far away. There's a lot of stuff in the way. And so we can learn more about how the actual universe formed and came together at these really early times. But as far as our place in the universe, to me it makes me feel very humble because the universe is so vast and weird, but also amazing in that we can just like sit here in this room and talk about it. And as humans, we can learn about these weird things that we can't use our eyes to see, but then we build a strange contraption in Louisiana and it figures it out for us. It's great.
The equations you put on the board, what are they, where do they come from, and how are you going about solving them?
Those are the fluid equations. I can go back to them. Are they back or forward? They're forward. These guys. So the top one is conservation of mass, and this one is conservation of momentum, and this one is conservation of energy, and this is the equation of state of the gas in the simulation. And so I'm glad I was Googling equations, and I was like, I better use some that I actually use, so I'm glad that I did that. So basically, these are just general equations where we say, okay, as long like mass has to be conserved, energy has to be conserved, momentum has to be conserved. These are general physical principles, and so you have to make sure that these are solved and these are met at each time in the simulation. And so you put in you put in forces like the gravitational force and any hydrodynamic forces. You put in the ability of gas to cool or to heat, prescriptions for star formation, and basically you try and make it as realistic as possible and emulate the real universe. And so when you make comparisons with the simulations that you get out and the actual galaxies, you can see if you're doing a good job or not. The code that I use is a smooth particle hydrodynamics code. It uses it's a tree code using n-body simulations. We can talk more about it later.
You mentioned
Where are we? Hi.
LISA is being built in Europe, did you say?
It's the European Space Agency is heading the construction, but some of it may be built at NASA because NASA is a partner with.
That was my question. Is NASA a partner, and is it a consortium of European country scientists or just?
Yes. So I'm a member of the NASA LISA study team, so I'm involved in the NASA aspect of LISA. And I'm not really building anything because I predict things and that's my contribution. But it hasn't quite been decided what actual contributions NASA will make, whether it will be in terms of engineering or hardware or technology or what, but NASA will definitely be a partner.
Thank you.
So I have a quick question. Would you be able to tell if gravitational waves are redshifted? Does that kind of language even make sense in this context?
Yes, gravitational waves are redshifted, which means that they get longer as the universe expands, and which happens to light too. We know a lot about that. It can also be gravitationally lensed, like light can. And so it acts like light, basically. It's a wave like light, except that it's made of gravity. It's a different force, but it's pretty similar. It also travels at the speed of light.
I'm not a scientist, I'm a writer, but I wonder, what's the purpose of you making predictions if Lisa's going to find everything else out anyway?
Because what Lisa gives us is going to be a bunch of those graphs with squiggly lines, but it's going to be kind of hard to interpret. Because not only is there going to be supermassive black holes merging, but there's going to be other stuff going on. It's going to pick up white dwarfs merging. It's going to pick up weird other merger events that I don't totally want to go into right now. But it's all going to be happening all at the same time. So it's going to get all of these things on top of each other. And remember, Lisa can't point, and so it's going to get them from the whole sky. And it's going to be really confusing. And so we need to make sure that we have a model for every possibility of what can happen. And some of the models that I have show a mass ratio of black holes merging that no one else has predicted, but makes a lot of sense. And now I've started presenting it at conferences, people are like, what? Oh no, we have to redo everything. And so apparently it's really important to make these predictions because otherwise when Lisa does give us data, we won't understand what the data says.
Hi, good afternoon.
I see you. Okay.
Does the scientific community hope to use this sort of detection as a window to understanding dark matter, since that is not detectable by anything in the electromagnetic spectrum?
Dark matter. Honestly, our best bet for detecting dark matter is probably the particle experiments that are going on in labs on Earth right now, because dark matter isn't expected to clump up enough to emit any gravitational waves. Only really compact things will emit gravitational waves, and dark matter, we think, is pretty fluffy. Again, we don't know, though, because we haven't detected dark matter, but we think it's some sort of weird particle that we just haven't detected, and people are building devices to detect this undetectable particle, because they think that's a good idea, not my field, it's good for them. It is really important to do, but yeah, this probably isn't a good way to detect dark matter.
A very good presentation, thank you. I just wondered if you could talk about how you developed an interest in this topic, and who or what has inspired you as you've pursued your academic and intellectual pursuits through graduate school and then here at Queensborough and in the other venues where you do your work?
That's another talk. That's a really big question. But sure. I decided to study black holes, honestly, because I started college in engineering, which is an admirable field, and I think it's really great, but it's not a good fit for me. And I wasn't happy as an engineer. And the day that I dropped my engineering major, I ran into a friend from high school, and he had also dropped his engineering major the year before, because he was a year ahead of me. And he said, well, I learned about black holes in my astrophysics class today. And I was like, wow, I'm going to do that. And then I did that. So it was kind of random, but I get very easily distracted and easily bored unless something is really, really interesting and cool. And no one can ever solve the universe. Even though I try every day, it's good job security because no one can ever do it. And so astronomers will always have something to do. But yeah, trying to tackle big, large-scale mysteries is just really excellent to me. And so after college, I joined the Peace Corps for a while, and I served in the Gambia for 2 years because I wanted to have adventures and do those sorts of things. And I came back, and I was like, I really miss learning about astronomy. And so I thought, well, I should go to graduate school then and see how that goes. And it went okay. So I'm still here. And my inspiration? I don't know. The universe is my inspiration. It's just so beautiful. It's really beautiful. I will never get tired of looking at it or thinking about it.
So I guess we could say that gravitational waves go through everything except maybe black holes. Like those are opaque to gravitational waves. They stop there.
They would go in, but they wouldn't come out again.
Okay.
Yeah.
So would diffraction happen around a black hole then of a gravitational wave, like a really big one, like?
Probably, yeah, yeah. Gravitational waves act like light, so diffraction would quite possibly happen. I never thought about that. I think more. I don't know about diffraction. Gravitational lensing would definitely happen in that light, as it goes around a black hole, will bend, and we've seen that with telescopes. And gravitational waves will also bend. And so as we start to detect gravitational waves from further and further away, which LIGO can't really do because it's limited, but LISA will be able to, we'll need to take into account the fact that gravitational waves emitted from one thing will probably have passed through some other thing that bent them before it gets to us. And we'll need to sort all of that out, which will be tough.
Well, along those lines then, is it possible that maybe dark matter would cause that kind of lensing to happen?
It could, because dark matter can be in really big masses, so it totally could.
Okay.
Yeah.
Cool.
You said that Einstein predicted this 100 years ago?
Yes, in 1915.
How was he able to do that? What led him into this?
He did a lot of math, is what Einstein did. It comes out of his relativity theory. So when he came up with special relativity and then general relativity, it's a result of that as things have gravitational energy, they can also lose gravitational energy through the emission of waves, which is what gravitational waves are. It's basically, as these black holes are orbiting each other, they get closer and closer and closer together, which means they're losing energy as they get closer together, and that energy has to go somewhere. And so the gravitational waves are what's taking the energy away.
Okay, you may have just started.
There, okay, hi.
You may have just started to answer the question, which is there a functional purpose for this in the universe? I mean, once these waves go off, is there a functional purpose, or is there a way we can use it for something other than to detect that it's telling us that an event happened?
Okay, so the functional purpose, I guess, is to help merging objects lose energy so that they can coalesce together. So if you happen to be a black hole in orbit with another black hole and you want to get closer, then you want the gravitational waves to help you get closer, and that's what they'll do. Can we harness this energy? I don't think so. First of all, we can't control where it comes from. We can't just like put black holes around and be like, okay, now you merge and then you merge. Like we can't really do that. Like, can't control the cosmos. And the amount of energy that we do get is so small. I mean, it took us 100 years to build a detector to try and detect it. And it's detecting this mass that's like wiggling back and forth less than the amount of a proton's nucleus. And so that's not any energy that we can get out of anything. And so it's a cool idea. And if we like had a binary black hole neighbor that we could get kind of close to, but not too close, we could possibly think about harvesting that energy. But that sounds dangerous and tricky. I'm not going to do that. Yeah.
Hi. I'm just curious. When you're talking about the gravitational waves, is it possible to block these waves and somehow, let's say that, I don't know, the crash between two different black holes block each other? Is it possible?
I don't think so. The only way to block, you can block light with like a solid object, obviously. But to block a gravitational wave, that solid object would need to be like a fraction of the size of the universe, probably. It would need to be enormous. You can also cancel light out the way I talked about the destructive interference. When you have light that's against itself, it can cancel out. But gravitational waves have more components. It's not just a one wave like this. It actually has a couple different directions to it. So to get it to cancel out would actually be very hard. And you would also need to have like an exact event like mirroring it. And yeah, I think it's possible to contrive such a thing, but it would never actually happen. So I don't think you can block these.
So if black holes form from dying stars, then they would not have been around in the very earliest start of the universe. It would have been later on in the life of the universe when stars formed and then had enough time to die that you would first have black holes. Is that right?
Correct, correct. Although some people do think that some black holes may have formed during the Big Bang through other processes. They're called primordial black holes. But I don't, maybe. But yes, in general, it takes a while for stars to form, and so then you wouldn't see any gravitational waves until you got some black holes, and then you have to wait for them to merge, which might take a while.
So then if you could go that far back to gravitational waves, you still couldn't go back to the Big Bang then, because you're saying there wouldn't have been gravitational waves until after.
But the Big Bang itself probably emits its own gravitational waves. There's like a zillion theories on what that might look like, and they're all different. And so that's another thing that people are going to be working on in the next 15 years or so before LISA launches, is what is the Big Bang going to look like in gravitational waves? Will we know it if we see it?
Thank you.
one up there.
Hello. I'm an artist by trade, but I'm not a scientist. So I was just wondering, can we ride these waves like we ride oceans?
That would be cool, wouldn't it? No, we can't. There's not anything to ride on, alas. But that would be cool. You could surf through space with gravitational waves. The solar surfer, maybe. Oh, the silver surfer? You should talk to this expert over here about superheroes, because she knows more about them than me.
Well, I want to thank Dr. Observatory and thank all of you for being with us. For a small reception right outside here. And again, on behalf of the college and our faculty, thank you very much for being part of this. And we hope to see you at other events, to be sure, in the near future. So thank you, and thank you, Dr.